We are after the first test. Not sure when that'll be done graded yet. Still working on it. But we're going to get into chapter 4 now. A little bit of Oktoberfest music in the background. Hope that's not too loud. Meanwhile, we're going to look at the first part of chapter 4. They've said that the goal is to get to chapter 8. So I'm going to be doing, I guess, about 3 sections per day, per lecture, to get to close to that goal. Chapter 4 starts off with explaining variation, introduction to explaining variation. Examining distributions of single variables is an important starting place, but we go beyond that and get to an intuitive definition of explain. So having a little bit of inside information helps you make a better guess about what something else is going to happen. That's a good thing. Sometimes the free information doesn't get you anywhere. So we'll kind of look at the differences between them, such as knowing gender. That can affect the answers to various things like thumb length or height or even weight, things like that. So knowing that somebody's female or male can make a difference in many cases. So having a female on the list that we know about says it explains some of the variation in height. Not all of it, but explains some of it because females tend to be shorter than males on average, but there are many, many exceptions, of course. So explaining variation can help us understand what causes the variation in a variable. It helps us predict, very important, future observations, or it helps us change the system we are studying to produce different outcomes. So we'll look at various things here in this chapter. I'm just kind of skimming the outside of that. So let's go to next. And it'll get there. Okay, here we are in 4.1. Explaining one variable with another. Let's start by looking at the distribution of thumb as I try to get a little closer look here. Write code to draw a histogram of thumb from the finger's data frame, and then you can, of course, change colors, etc., etc. So what I decided to do here, and this always works better if you've tried these in advance before you watch the video or before you show up to the lecture. I know not everybody can do that, so I try not to give too much away, but I am doing quite a lot here. So please try to work on this in advance or work on it simultaneously with me, and you can see how it may go, and you may be able to compare your notes with mine. But for you just to follow what I'm doing only would not be the best way to understand this. So I just wanted to put that caveat out there. So we're going to get the data by variable thumb from the fingers data set. And we're going to fill with whatever color. So I picked red, just to be a little bit more dramatic. Let's go over and continue. You can do color blue, so that's the outside color. It always seemed a little bit misleading to me. The fill is the main color, so that's what you mostly see. Then I decided, just because they said something about bins, let's try bins equals 20. Just a number I picked out of the blue. Let's go ahead and submit that or run it. You'll be submitting. So here's what we have. This is data we've looked at before. And we can see the thumb lengths ranging from 40 millimeters up to 90 or so, and much more dramatic coloring, I think. But I picked 20 bins, and they apparently picked something else. As you can see, their distribution is a little bit different than mine. If you compare them side by side, I've got it zoomed in so it's hard to do, but you can see you've got different peaks here, whereas over here in the other one, which I believe has 25 bins, I believe I counted them, still have a couple of peaks, but it looks a little bit different just because of random chance. Sometimes one of the bins will kind of zero out. The more bins you have, the more likely this is apt to occur. The less bins you have, the smoother it'll look like, but if you make it look too blocky, like with 10 bins or 5 bins, then you've lost some of the information too. There really is more an art than a science to try to pick the best looking histogram. So what I do is I just kind of keep it simple and pick even numbers like 20, 25, 10, 15, things like that that are standard numbers. I wouldn't pick a 13.5 or something unless I had a really special reason to do that. So anyway, you play around the number of bins. The shape will look a little different. It's the same information though, and sometimes you could get shapes that look really different, but that's very unusual and not likely to occur. Do not be concerned about that, but it has been known to happen. We have seen this, we've already seen this a few times, is what I'm trying to say. And we want to use some other variable to explain the variation we see in thumb length. And a starting place is to think about other variables. That if we knew somebody's score on that variable would help us make a better guess about their thumb length. And of course, the one we've highlighted is gender or sex. One is female, two is male, and then you even have a third option, which we're not really looking at. We have by race. We have by the year in school. Math anxious. Do you agree with this statement? I'm very anxious. 2, strongly agree. 1, agrees. 0, neutral. And then we had these odd numbers. We're not really looking at this data set, but -1 for disagree and -2 for strongly disagree. In other words, they don't feel anxious at all about math. So good for them. Grade predict. Now, I'm not sure this may be the predicted grade they think they're going to get in the class. They weren't too clear about that. Ring, of course, is length in millimeters from the tip of the ring finger to the crease between the ring finger and the palm. That seems like that might be tied into the thumb pretty well, and height and weight could be done. So here, we'd like to kind of choose the variables that might be best. And the thing is, the year in school would have little difference because people are pretty much grown up, assuming these are college students. Not too much growing left to be done, maybe a little bit. Anxiety of math has nothing to do with your fingers, and the grade you get has nothing to do with your fingers. However, the others just may have something to do with that. And do you think that gender or sex could explain some of the variation in thumb length? Well, because men tend to be bigger than women, I'd say so, yes. Not completely, of course, but because women are smaller than men on average, perhaps their thumb lengths are smaller also. Seems kind of obvious, to be honest. One variable that might explain the variation in thumb lengths is the gender. So we might intuitively think, and we've already gone through this, they would differ, they would vary. But even amongst a bunch of females, their thumb lengths vary as well. And can we see how thumb lengths vary by sex in the histogram we made? Well, taking a quick look back here, no, we can't, because all the people were put in together, all of them. So there you are. This is for the first lecture of the week, by the way. I don't have my calendar in front of me. I meant to give that as an introduction, but in case anybody is looking at the wrong video, this is the video following test number 1, scheduled for October 5 and October 6. And we'll be back on October 7 and 8 live with more on Chapter 4, explaining variation. Okay, here's a nice picture here. The variable sex was not included in the previous histogram, but we can visualize the relationship between thumb and sex in a few ways. And here's an interesting way of doing it. They've gone ahead and split it up by sex and assigning females one color and males another. They've used the fill command for that. And I've got my cheat sheet pulled up anytime I need it. It does help sometimes. So fill by variable with a tilde sex. Now they've picked some default colors, and male is kind of in this blue-green, and female is sort of in this red. And one thing that's striking here is that the males, there are a lot less males in this data set than females. So almost every step of the way it's smaller, just a couple of exceptions, and out there it hardly matters. This is the thumb length. And it's a little difficult to see much from this, but they have some explanation here. They say it's a bit of a pain to change the default colors, but if you really hate these colors, and I'm not a huge fan of these, you could change it. And so they have a way to do that if you were interested in that. You're not really responsible for this, but just in case you did use this for some sort of project or thesis, it could be helpful to pick what you want. So what they've done here is they've got the thumb, the data fingers, and fill with the sex, and then they chain it with the percentages and the greater than, and they have this new command, and it seems like a lot of work, scale fill manual, values of purple and orange. And so we could do the color as well. So the fill is more visual. The color would give the framing on the outside. So that one isn't, to me, quite as important. But otherwise, it's exactly the same. It's GF refine. So it says we don't want the standard coloring. So they both use GF refine. So here, we can change the fill colors used to the different values of sex, female and male, in the histogram we made before. So let's see what we could do about that. We could go back and take a look at the stuff. We already have, by the way, the fill sex already there on the first line. All this first line back here is exactly the same. So I'm going to chain it and copy only that part forward. Don't need to say it twice. So I'm going to copy and put that into paste. And let's just see what happens when we run this. They have a hint, of course, but let's just go ahead and run it. And oh, there it is, purple and orange. And so I thought about changing it to Laker colors. After all, the Lakers, as of this recording, are doing quite well in the finals. First time in a few years. Glad to see it. So let's change this to yellow just to see how it might change just a little bit. I run it again. Oh, okay. Same histogram, different color. Perhaps this one's a little bit too stark a contrast. I don't know. It looks like this is almost disconnected, and the orange might have kept it connected just a tad better. So anyway, this was their larger graph with the orange coloring. So still shows the same information as it was with red and green, but there's still a lot less males than females. So that could be considered to be a bit of an issue. You might notice that the males are slid over to the right a little bit and the females are slightly to the left, but it doesn't seem to be extremely significant. And by the way, if you were to run the second command with the color command, which is just the framing on the outside, all it would do is just change the framing on the outside. So that, to me, that isn't quite as important, but they sometimes make a big deal out of that. Okay, another way to examine the male and female data is split the histogram made into two, one for females and one made for males. Have two separate histograms, and so what they have is GF facet grid instead. So we could try that instead and see what happens. Let's see, we've got the thumb, data fingers, and all that. And let's see, they actually haven't asked us to do that yet, so we'll postpone that discussion for a while. Let's just take a look at what happens. And here I've got it zoomed in a little too tightly, so maybe I need to zoom back so we can take a slightly better look at it. So the thumb lengths are what we're comparing, and it really is zoomed. But there's the female, there's the male. And female, there's a lot more of them. And the male, there's a lot less of them. It seems to be stretched quite a bit on the high side, vertically stretched. So it's a little hard to get one good look at it. But anyway, it's tough to kind of compare these. This is even tougher than the original combined set. When the thumb lengths vary by sex, yes they do, but it's tough to see. It's not easy to compare them. You have to look very carefully and look for what you think the center is and all that kind of thing. So would it be more helpful if they were stacked vertically, one on top of the other? Absolutely. It would look a lot better. In fact, they're going to do that next. So they have some commands to do that, and histogram with thumb data equals fingers. And so they're going to use the facet grid by sex, but notice sex tilde dot. That's a little bit different. And so what that does is it puts the females on top and the males on the bottom, still by thumb length, being arranged along the x-axis, and the counts, which are the same, being listed from 0 to a little past 20. And now you can definitely see the shift. The females are shifted a little bit to the left, the males are shifted a little bit to the right, if you imagine where the center would be. And yeah, that's the best one of all so far. This is more helpful than side by side, just easier to compare them. And it's immediately apparent, as we already noticed, there are a lot less males than females. So maybe density would be better for this one. Let's take a look at GF, and let's try density histogram here instead. So we'll just slip a D in front of the histogram, and it looks like we chained that with facet grid. And remember, we always lead off with the Y variable tilde X variable. So I could just say that to remind you of this. I'll put the pound sign so it doesn't interpret it as a command. I'll just say parentheses Y and then tilde X. This is how I remember it. Y goes first, X goes second. X, of course, X-axis like the thumb, and the Y could be the count. So that's just my little explanation for that. Let's go ahead and run this and see what happens. It should be the same as before. The only difference is we have the density, the proportion, which could, if you wanted, convert to percent very easily. 0.04 is 4%, 8%, 12%, etc., if you wanted to. There's the full graph there. They probably have a better picture down here. Let's look at the zoomed up picture here. I have to zoom back because this is already pretty much zoomed. And now you can definitely see the shape shifting. So there we go. The females on top, males on the bottom. But then the density kind of makes up for the lack of people in the male survey. So Now this bar has been pulled vertically up higher, more than 12%. And this one, which used to be pretty high, is now only about 8 to 10%. So that seems to have adjusted for the lack of males or the abundance of females, or just to get the sample sizes to be equal, so to speak. And you can see a little bit more about the spread, apparently, and certainly the shift to the right is still obviously there. All that's done is just pull higher on the vertical, or crush down a little lower on the vertical side for the females, just to standardize it with the males. And of course, thumb lengths vary by sex. The males are bigger on average. And there's still variation. It isn't like suddenly all males have the same thumb length. No, that's absurd. So what we have here is variation. Of course, there's a thumb length variation. However, it can be stated, and they will state this if they haven't already, that once you start splitting it up by these categories, you have less variation within the groups. Now, I'm not going to really big deal out of that because you can't really see it here in this sample set anyway. But there's a little less variability here. The males, they don't go less than that number, 45, 46, whereas the females do. But then you have some rather big-handed females as well, so that spread didn't change much. With the males, I think you can see that has definitely changed for the spread. So yeah, still variation, of course. Another way of thinking about sex, explaining variation in thumb, is to say that thumb is really made up of two different distributions, one for males, one for females. And yeah, you can do that. It happens quite a lot when it comes to physical characteristics. And there are both males and females with longer thumbs, both males and females with shorter thumbs. Now, I'm not sure if this video would play, plus it really is up to you to play this video. Let me just see if I can get some of the highlights from G, who's the author and also the leader of the group that I've been going to. Let's just see if this will play. So as you see, we have some video for you to watch, and it goes through all kinds of stuff here. And I can just little snippets here. She's got some graphs here, the females and the males, and she's looking at it backwards clearly, so she has to be thinking outside of the box to get to it. So this is something that you should be looking at to enhance your understanding of this particular section. So I'll let you watch that. I have plenty to cover today besides just replaying this for you. We know you can play this yourself. Where should you use in the histogram? Look in the histogram to notice within group variation. Well, the spread. I think the spread is pretty clearly the way to go, and you could look at the various ones to see the variation. The center would be see which one's larger. The males are larger, but the spread is what we're really looking for. Density doesn't have too much to do with it, and skew doesn't have too much to do with it. When we combine all the thumbs together in a single histogram, we are able to see how spread out the overall distribution is. Sorry about that. This gives us an idea of the total variation. And anyway, the sum of the variation for thumb has been accounted for by sex or gender. And we can only see the within group variation after we divide the distribution up by the various groups. In this case, it was sex. And we have other variation called leftover variation. She calls it other stuff in her video. She's very informal, which is nice, in many ways very refreshing. So anyway, we can take a look at some of these, and they took the density, which kind of puts a smoother curve over it, kind of like a weighted average, so you can get a little bit of a better look. And now it becomes very clear that the males have bigger thumb lengths than the females. The peak is much further to the right than the left. Just in case you couldn't figure it out, that command, the density command, would help you with that. And you of course can adjust color and fill as usual. Here they picked to fill it with orange and color it with gray, so gray is the outside marking, and they did that, and they did it by the sex, of course, and they did it with the density histogram, so we could kind of neutralize the sample size difference. So we have a few multiple choice questions. Let me see if I have a few comments on them, not to answer them for you, but you've learned to make some pretty fancy histograms now. Let's reflect. What kind of variables should go in facet grid? This is meant for the categorical variables. But histogram, on the other hand, is just the opposite of that. Tally gets us back to categorical variables again. And the variables you think would be worse than sex, the ones that have nothing or little to do with thumb length? Well, height would probably have a lot to do with it. Pinky probably would have a lot to do with it. But your job, really? The year of school you're in? No. Race, maybe a little, but not apparently a lot. Gender has much more to do with it than that. So we can make a grid of histograms that we could try to do to investigate the association of the variable we chose with thumb length. Make sure you use a categorical variable. So let's look at the request here. Write code to create panel density histograms of thumb to explore variables that would do a poor job of explaining variation. And so let's say we picked the job, the year, and even race ethnic, which may have a little something to do with it, but not as much as you might guess. Let's take a look at what we could do for that. By the way, there's a hint here. What does the hint say? Oh, not that one, but let's try with this thing. Use str. Well, it turns out I didn't really use that. So instead, they kind of tipped their hand and gave you the answer back here. So why don't I just go ahead and take a look. First of all, we set up the histogram with the tilde thumb, that's the variable, data from the fingers data set, and the chain says we're going to look at 3 different items: the year in school, the race ethnic, and also we're going to look at facet grid. And they didn't even look at job at all, so we're just going to look at those 2. So I'm going to copy those, and let's go ahead and put them in here and see what happens when we run that. Takes a moment to think about it, but we have a couple of different plots here. Let's take a look at them in order. The previous plot, this is done by, I guess that's the first one we did, which was the year. So here's the first year. Here they are. You can barely see it. 1, 2, 3, 4. And you can see that here's the freshmen, sophomores, the juniors, and then there's like 1 senior. And they have a better look down here. So why don't I just go ahead and jump down here because it's the same thing. Yeah, I don't see much change. We have simply more sophomores than anybody else. So yeah, it's a little bit more spread out just because of the sheer numbers. And there's only like 1 senior. So that's not much variation at all. Well, I don't see anything that distinguishes between them except for more data. And one could neutralize that with a density plot. But the trouble with that, with only 1 person, you get 100% on this one. And that would be a really large spike. So that would be kind of maybe not a good choice in that extreme kind of case. Well, as we already quickly looked at, as we found the plots that apparently they just generate the colors automatically. They didn't explain how that happened. But now we can take a look at various races, and the white, the African American, the Asian, the Latino, and then other. Doesn't seem to have a lot of shifting going on. They've already done this by density, by the way, so that's something subtle difference. They did not do density for the first group. They did do it for the second group. I don't see any significant difference. Other seems to be slightly to the right, but there's just not that much information there. So of the 2 variables used to create the histograms above, years and race, which does a better job in predicting thumb length? Year, race, they both seem good, neither seem good. I don't think either one of them look real good. You could split hairs and pick one, but I don't really see it. Maybe race is just slightly better than year, but not by very much. Here we have another video. Let's just take a quick look at it. Okay, so I'm not sure if this is even recording sound-wise. Last time I tried to do a video, the sound did not record, so I'm not going to play that out. It's a short one anyway. So yeah, the gender, the sex has something to do with it. The years don't seem to have very much to do with it. One could find out minor differences, but I'd have to say they're minor. So anyway, you look and see if there's a shift or not. That's the biggest thing. So let's get to the next one, 4.2. Looks like 4.1 was probably the longest one. So let's go to 4.2, one that's sort of long. 4.3 is a shorter one. Outcome and explanatory variables. In other words, outcome is y, and explanatory has an x in it. That's how you know that's the x variable. I still have to remind myself of that because I just don't think this way. I've always thought in terms of x and y. Can't get it to zoom out. Don't want to zoom out too much. So we have a sense of what it means to explain variation in one variable by variation in another by isolating some information and seeing if it helps us or not. Does the year help us? No. Does the gender help us? Does sex help us? Yes. So that's something we can certainly look at. And we have the two outcome variable and the explanatory variable. In our example about thumb length and sex, what was the outcome variable? Well, in this particular case, the outcome variable is y, and that's the thumb. That's what we were interested in, is the thumb length. The sex is what we used to explain it. That was the explaining variable, the input, the x, and the output was the thumb length. And they have others. Our example about thumb length and sex was the explanatory variable. Well, in this case, the explanatory variable would be x, and that would be the gender. So yeah, sex, the gender, explains the thumb length. So they're just drawing this out into a long pair of questions, but that's really all it is. They have other words that sometimes are used, independent and dependent. I would have started with x and then y, but they did it the other way around. Outcome variable. It could be thought of, the y could be dependent on the x. The x is over here. Explanatory variable. Independent variable. You choose that one. And y comes from that. So we predictor and we get predicted variable, a treatment variable, a response variable. That's very easy to see that. Experimental variable factor, output variable. All the y words seem to be easier to understand than the x words, but you do have to start somewhere. And so that's how they do that. There are several words there. And we have lots of fill in the blanks this time, I guess. So I'll largely let you do that. Just put something down. Don't leave them blank, please, because I would notice that as I start to tally up your points. And by the way, you do have all the way to December to finish all of these, but we hope that you're doing them before the tests and in a regular way, like weekly, like about when the lecture is hitting, either live or recorded. We hope you're not putting these all off to the end. That would not be a good way to go, but I'm sure most of you are aware of that. And a few of you have already dived into Chapter 4, which is fully available, and very soon I'll be opening up Chapter 5. My best guess for the next test, by the way, as I get off track a little bit, would be 4 or 5 in the first half of Chapter 6, but I have not heard anything official. They did not have a meeting last week, so that's how I would do it. But we'll see how far we get into Chapter 6. Maybe we won't even do that. I don't know. Anyway, we previously learned that categorical variables should go into the facet grid type of command. And now we know that sex is not only categorical, it's also the x value too. Why is it useful to split it up by the x variable? Well, yeah, so you can see the differences. That's kind of easy. Males versus females. Now, the quantitative numerical variable should go in the histogram. Does that mean that only quantitative variables can be outcome variables? No, you could have categorical variables be outcome variables too. And so they answer the question right here. Yes, you can. It's just they wouldn't be on a histogram. So what kind of visualization would be most appropriate for that? Well, it looks like a bar chart would be better for that. It looks like a histogram, but it's got categories underneath it, sometimes called a Pareto chart, which they are not using here. I can't seem to expand this. This pad doesn't always work for me. I know you'd like to see it a little bit bigger if possible. So if I can make it just big enough, it's tough to do. Okay, so it's important to figure out whether it's quantitative numerical or categories, categorical, sometimes called qualitative, but that's too confusing. And it's equally important to see whether it's X for explanatory or Y for outcome. And so making this last distinction requires a greater understanding. There are occasions, they actually show one, where the X and the Y could be interchanged. It's possible to do that, but nearly always it's best to do it one way versus the other. So we don't want to do that. We are trying to predict a Y based on an X, not usually the other way around. So back in this Mindset Matters, they had the housekeepers and they told some of them that what they do satisfies the recommendations for an active lifestyle. And the others were not told anything. So then they did put a condition whether they were informed. These 6 people were uninformed. And then they also measured whether they lost weight or did not lose weight. Now, not losing weight would mean either you stayed the same or gained weight. So lost weight had to be losing weight. I don't know what the criteria was. Is it by pounds? Is it by tenths of a pound? I just don't know. They used the head command and they selected the variable data frame and then condition, then weight loss. So that's just how they did it for a listing type of a deal. The outcome variable was the weight loss. That's what they're interested in, whether they lost or not, and that's a kind of a yes or no situation. So they'd like us to write some code. We have a couple of R's to do here, so let's see if we can figure that out. One could actually check the hint if you'd like, never a problem. Think about the types of variable, what type of graph would be best. We've learned about GF histogram, GF bar. Looks like GF bar might be the best way to go, so I'm going to go back in here and type in GF underscore bar, and then go to the parentheses, and I'm going to type in tilde weight lost. That is a actual variable. I'm going to put comma, and then we're going to talk about data from Mindset Matters. So that just gets us into the correct data frame. Make sure everything is capitalized where it's supposed to be, and that should be it. Let's just see what happens when I hit run on this. Of course, you'll want to submit your work so I can check it out. And so all we get is here are the people just found that they lost weight or didn't lose weight. So ones on the left lost weight, the ones that didn't lose weight were on the right. And there you are. And they have a much bigger picture than I do, but it's essentially the same. This is by count, of course. Almost 50 on the left, almost 30 on the right. That's basically what I got, so that's the same. So we used a bar graph to visualize the distribution of weight loss. And the condition is the explanatory variable. Why is condition considered the explanatory variable? That's what we started with. The condition, remember the condition was either informed or uninformed, and so that is not reflected yet in our graph. So yeah, let's go to GF facet grid with any plot, not just histograms. Try creating a bar graph of weight loss, but chain on a facet grid to compare the outcome across conditions. So that's something we didn't do before. So let's see if we can copy what we just had. So I've already got that stored. Oh, that's actually wrong, so I apologize. Let's go ahead and delete all of that. My apologies, delete. Let's go back and copy this part. Here we are. And get started with that. We don't have to type everything in all the time, as you well know. And let's go back here and get that put in there. Command V. Okay, now we're going to chain that. We don't need to see this again. We just did it. So let's go ahead and use the percentages greater than percentage. It's just a chaining. Oops, that's a percent. And one could skip down to another row if you'd like. And this is going to be GF underscore facet underscore graph, just like they said, or grid, I'm sorry, I could have just copied that part, I suppose, grid, and now parentheses, and condition. Condition is what we're going to be discussing. That's the X, and tilde with a dot, which is sort of a neutral way of just saying use what we already put in, the weight loss. So now if we go ahead and make sure facet is spelled correctly, it will notice every little thing that's wrong. And of course you have a hint here. Don't forget to create a facet grid by condition, so I just tried to do that. Let's run it. And now we have it split up. And let's look at the better picture down below, much bigger to see. And notice they've said informed. The informed people, and looking at the bottom for the X, informed people tended to lose some weight. They lost a lot of weight because they said, oh, I've got a job here that helps me lose weight. I'm going to just keep on doing that. And a few people couldn't lose weight. However, the people who were uninformed didn't really have that going for them. They're like the placebo effect. Some of them still lost weight just naturally, and others didn't, but it was closer to 50-50, although, generally speaking, they still lost weight. This is an active job. So no matter what, whether you're informed or not, looks like you're losing weight on average with a small sample size. But even more so if you realize, hey, I'm getting brownie points from the Surgeon General. I think I'm going to do even better and lose even more weight. And so many of them, more than a 2-to-1 ratio, were able to lose weight because of that. That's my thinking behind this. They did not use that way of thinking, but I'm trying to get to a kind of a meta summary of what might have happened here. Anyway, there's a real limitation in this graph. The sample sizes are different between the two groups. You have to look at the relative difference in percentage of housekeeping who lost weight. So a tally could be done, and they could do a density histogram. So what they didn't look at the raw numbers. They looked at in terms of a proportion, although 7 decimal places is a bit much. We do have the informed people, and they've got it kind of arranged not parallel to the graph. So informed group, 68% versus about 32%. That stands for the first two going across, the 68 to 32, 68%, 32%, more than 2-to-1 as I mentioned. Now you look at the uninformed, which is slanting the other way on the tally, going up, down this way, 59% lost, not 68, so not quite as good. 41% did not lose because, of course, it adds up to 100%. So that was closer to 50-50, although still being an active job, people tend to lose weight no matter what. It's just you've got that double happening here when you see, oh, I really am losing weight. And the Surgeon General said so. I'm going to just keep this going and work on my diet as I work on my job. Anyway, some people are lucky enough to be able to do that. You've explored examples of 3 of the following variables. Which one have we not yet explored? Now, this one seems to be a bit off-center to me, and I don't believe this could possibly be any kind of a test question. Plus, I do get to choose from a field list of test questions. There were 47 I could have chosen from. I picked 20. I did not go out of my way to pick the hardest ones, by the way. So hopefully most people did pretty well on that exam. I may be under a little pressure to pick slightly harder problems next time. So just a word of warning. But I don't think these really fall into that kind of grouping. But they tell me that quantitative explanatory is one we did not talk about. And it is possible, yes. Let's continue, though. And we've considered both quantitative, the numerical stuff with the thumb, and categorical, like the weight loss, which is just talking about the number of people. It didn't say how many pounds they lost. It just said how many people fell into these categories. And they did a cross-section by whether they knew about the Surgeon General's comments or not. So we had some categorical explanatory variables. And we could look at the quantitative explanatory variables. So they go in a little bit into detail on this. And she uses the other stuff here because that's just miscellaneous, random error, and other things we're not talking about yet. But the weight loss could be, supplied by the condition that they knew informed versus uninformed and other stuff. And here looks like the best one would be a tally because we're just tallying people. And you could do for counts or proportion. I'd say proportion is probably the best, but they didn't ask that question. What outcome variable does this include? I would say categorical, because that's what we're doing, categorizing these things. And that's the Y variable, the outcome. The explanatory, which sounds like an X, that's going to be categorical as well. So really we're talking about 2 categorical situations right here. Now consider another one. Thumb equals gender, sex, or in addition to other stuff, because there is some randomness, of course. Not everybody's exactly the same. And so the best one here would be the histogram. And we've actually done that already. What kind of outcome variable does that include? That's the Y, and that would be a quantitative, numerical Y outcome variable. The explanatory variable is a categorical one, because that started with the gender, the sex. So that's how they started it. So they're getting into all this kind of stuff that I'm frankly, well, I know it's necessary, but am I super impressed by it? We've got much bigger fish to fry than this. But let's see if we can get you through this so you can learn a little something from it. And the best visualization here on this one, thumb and equals height and other stuff. It turns out that neither one of these is very good to use. You can try them, but neither one is great. The outcome variable for this one is the quantitative variable. These are all numerical type of deals. And same with the X value. It's also quantitative. So that's basically how those could be described. And so if you wanted to explore a situation in which the explanatory variable is categorical, which are true. I probably should let you try that, but 2 of them are true and 2 of them are not true. This one I will let you fend for yourself based on some information that we've had already. This is not part of the chapter test. Just see what you get and see how well you did when you're done. So then you can submit when you're done. I'm going to go ahead and zoom back and go to the final of our 3 lessons today. 4.3, more ways to visualize relationships. Point and jitter plots. I had never actually used jitter plots before. I was only vaguely aware of them. With the Masters in Statistics, we had other things to worry about, but this is still interesting, and it does provide a quick and easy way of describing certain types of data. We have learned how to make visualizations of outcome variables as a result of X variables, and histograms and bar charts, and et cetera, et cetera. So we learn a few more here. Scatter plot is a common way to show the relationship between an outcome, a Y, and an explanatory, an X. Scatter plot would show each data point as a dot on a graph. And a scatter plot in GG formula can be made with the function GF point. Let's try using GF point to examine thumb lengths by gender. So this is just, all the different people by female and male by the thumb length. This is similar to before, except it's going from bottom to top, vertically speaking. And the males tend to be a little bit more than the females. And so it's just another way to look at it. Not my favorite way to look at it, but it's certainly one way to do it. They let, Y is thumb, X is sex, and data came from the fingers data set. But they can change this all around, and boy, do they ever. You can, of course, change the color, although I'm not too fond about this color orange, but you can do that. And all they've done is they put in the color equals orange. And they have a size command. What does 5 mean? Well, 5 is certainly bigger than whatever the default was. It's wider. Trouble is, though, they tend to overlap so much. I don't find that to be particularly interesting. The size is too big. Before, they kind of mostly stayed out of each other's way, although there was some overlap there. Surprisingly, they all kind of stayed out of each other's way, but not here. Okay, here's a question. When we compared thumb length using faceted histograms, thumb appeared on the x-axis on the scatter plot above. Thumb appears on the y-axis. They wanted us to see that. Before, thumb was on the x. Now it's on the y. Interesting. So you can drag that over. What does a point represent in a scatter plot? Well, it says here of observational units values, a student's thumb length and the sex. Yeah, so all the others are not really the same thing. A data frame is the entire set of data not really broken down. And here we just broke it down by sex. Here we just have all these are missing something. This D finally gets to the heart of the matter. So that's why they're doing it. Well, the problem with the GF point, of course, you can't tell when a point is on top of another point. This is something I'd never really done before, but it's possible to do. You can jitter these points around, move them left and right a little bit, and even up and down later. We can see all the individual points better, so that's what they did. They put in GF jitter, apparently some default commands, and that's all they did. And now you can see this is exactly the same data set as before, except it's been moved back and forth. And this very popular value, looks like 55 for the females, has been moved from left to right. And the left-right does not mean anything. It's just they're keeping out of each other's way. And even then, these are almost on top of each other. So the jitter command didn't do a perfect job, but it did a much better job of keeping these out of each other's way. So the left-right means nothing. It's only up and down we care about. And they seem to be jittered randomly, by the way. So to me, that's not really mathematical, but it does improve the look of certain pictures. But I like the histograms better anyway. That's my personal opinion. So we could play with a few things just to modify it. And so, of course, they use color. They love orange. And you can use argument height to change how they get up and down vertically shifted, too. So turns out they didn't really do that because they put height equals 0. So they didn't allow for that. They will do that later, or I'll do that later. And so all they really did was they just changed the color. So this is the same graph as before. You can look back here. It's exactly the same. I don't see any difference. Well, okay, the jitter being random, yes, there is a difference, but the data is the same. The data is the same. There's still a lot of 55s, maybe in a slightly different ordering because of the randomness of the jittering. And so it's like a little snapshot of where these are jittered back and forth. So you just take a snapshot. And yeah, so it's a little bit different, but not terribly so. The vertical length is still the important item. Now width changes how the points get jittered horizontally, that is left and right. So here we can tighten it up a bit. So the width now being 0.1 just shrinks the jitterishness. But the thing is, 55, a lot of them are clumped together here. So maybe this wasn't a good choice, but personally I don't mind this. It's a little bit easier to look at, in my personal opinion. But anyway, that's the idea for that. What do you think it might mean if one female point is a little to the left of another one? As we kind of said before, all these are in the 50 levels I'm pointing here. They're all 50, and that one is the same as that one. They're all in a kind of a five-way tie to the nearest unit, which is probably whole units here. I don't think they've gone into decimals on this one. And the 55 being very popular. All these are just the same. There's maybe a dozen or so in that little clumpy area. Okay, now we have a little bit of multiple choice, and we could take a look at this histogram. The height of the bars tells you how many people there are with the thumb length. Yes, that's how a histogram would work. That's my preference, is the histogram. And the jitter plot, what tells you about how many people there are with a particular thumb length. Now you go for the row. The number of dots in a row would be what we're looking at. So we just kind of zeroed in on that. So they're just kind of reinforcing. Here's the 55. All the dots in a row. It's hard to count them because they're still kind of overlapped a lot. You can go back and count the other ones. And that would be how it would go. Part C. And of course, you can make your guess. I probably shouldn't give so many of the answers away. I should probably let you discover them on your own. In a jitter plot, a dense row plot shows there are a lot of people with that thumb length. And then we talked about the 60 and the 55. More points means more people with that particular thumb length. And you can change the size of the points. For some reason, these are too small a dot for you. There's not enough of an overlap. You can make it even more overlapped. So they picked a size equals 5, which is more than the default, whatever that is. Now we have another kind of thing going on. We've got a width of 0.05, so the width is changing. We even did not change the height, so that's not going up and down, but it is going back and forth in a very small way. So let's just isolate width first of all. I don't want to do too many things at once. Before we had width of 0.1. And so it kind of stayed in a narrow group, and 0.05 is half of that. And so it's shrunk the sway for the jitter even smaller than that. The size has grown. Of course, we're still in orange. Alpha is another one. They're doing several things at once here as we wind things up just about. This has to do with the opaqueness. 0 is super transparent. 1 is opaque, so it'd be like a solid dot. And here they picked a 0.2. So that means that by itself, it's pretty see-through-ish. 0, I think, might mean you couldn't see it at all or be so faint. And this question here in the jitter plot above, which makes use of transparency, what visual features indicates a higher frequency of data points? Well, if you have less transparency so you can see it, so they kind of did a double negative on that one. Transparent, we want less of that. We want to see the dots. So transparency says you can't see it. And something like this is quite transparent. You can't see that very well. So we have another R to work with here. Play around with GF jitter. So there's so many things we could do with this one. And you can do all kinds of situations here. So I'm going to try to do that now. GF underscore jitter, parentheses. And we like to kind of borrow from before. I'm just going to take some of these and then just change them around a little bit. So I got this all copied. I already typed in GF jitter. That's okay. So let's just go ahead and erase this, delete. And then I'll go ahead and paste that over there. Oh, didn't like that. So I didn't apparently copy that correctly. Sorry to waste your time. Let's do it one more time. And you may do the same thing. Go over here and get that whole line and copy and paste. And here we go inside the box and paste. And there it is. Now I'm going to change a few things around. For example, not thrilled with orange, so I'm going to change it to blue. This is really not very important, except if you feel that the color you have doesn't explain things well. And I decided to change the size to like a 3, just make it a little bit smaller. I also wanted to make the opaqueness go up a little bit, so I made it 0.5. And width, what did I do with width? I changed it to 0.07. And Actually even changed the height a little bit, although they didn't change the height at all. But what happens if you change the height? It makes it go up and down a little bit. So maybe I shouldn't do that. That seems to change the variable stuff. In certain cases, that could be helpful, but I'm not going to do that. Instead, I'm just going to run this to see what happens. And so here we have a picture here. And so you see the width has been widened a bit. The opaqueness is a little darker. Of course, I changed it to blue. Of course, it's not stretched out too much either. And they came up with something else, of course. This is what they got. And what they're doing is looking at the entirety of the data. So that's a little different thing. So this is really comparable to female versus male. The gender, the sex has cut the data kind of in half, into two pieces at least. And you can see the various changes. So change it around on yours and see what you can come up with. Different colors, of course, different sizes, different alphas. Just play it around with it. No big deal. So no restriction on what kind of variable you could put in the x or y axis. So we could switch that, and instead of thumb sex, thumb tilde sex, thumb being y and sex being x, because it's always y tilde x. What if they switched it and sex tilde thumb? All that happened was they have the males, and yes, they have the sex, of course. The males are on top and the females are on the bottom. But now they have the advantage of having the thumb going from smallest to largest. In some ways, I think this is actually better. So here they've got it up and down. Here they have it left and right. Here the males on top, females there on the bottom. And so there's how it goes. So even though you can put the outcome variable anywhere, it's more common to put the outcome variable on the y-axis. So this is a better way to go here. And the jitter plots conforms with what people expect, makes them easier to interpret. So y going to x is always outcome for y, explanatory for x. A is clearly the correct answer. Okay, that'll do it for today's lecture. We've got the 3 sections. I expect to get to 3 more in the live lecture coming up next Wednesday and Thursday. Don't know when the tests will be graded. I still have to do various things. Like, for example, instead of grading yesterday, I had to plan out the rest of the semester. And it's a sliding scale here because they keep changing what chapters we're going to cover. And that's out of my control. So I'm just doing my best to be sure we're covered. If I go a little fast in the beginning and slow it down at the end, okay, you can always check the cloud links for the live lectures. You can check, of course, these videos again and try it on your own and use the video as an aid along with it if you need it. And that's how we hope that you'll learn this stuff. And hopefully things will going okay for you. It's still very warm out, but we hear it's supposed to be in the 80s next week, and I can't wait for fall. The Oktoberfest doesn't quite put me in the fall mood yet, so we'll let you go, and we'll talk to you live on Wednesday or Thursday, depending on what section you're in. So have a nice day.